Great, it's recording now. So let's start with this Desmos activity 1, limits and continuity. If you click on the link that I just shared with you guys, then you will look at this screen, right? If you just want to go over the activity once, you can click here, continue without signing in. You can do that now, just so you get a, an idea of how the activity is. But later on, I would recommend that you guys create a account in Desmos.com, which is OER organization free, so that your work will be safe and you can improve it. And in the end, I will grade the last submission. Okay. Yeah, but let's say we want to just start directly here. You click in there, and then you just type your name, first name, last name, right? I'm gonna enter as a famous English mathematician, considered to be the father of computer science, Alan Turing this time, Alan Turing. Alan Turing. All right, so, and then I will click on go, and then the first challenge will come up. Welcome, Karen. So in case you want to join us with this activity that we're gonna go over for the first 20 minutes of this lecture, just click on the link, please, and then you will be shown a screen. Click in start without signing, and then you will begin the first challenge. First challenge is watch this dot as it moves along the function y equal f of x. What y value is the dot getting closer to as x approaches 1 from the left? Look, from the left. If you figure this out, please write it on the chat, or you can say it too, right? Anybody can say,
Is that 2?
Excellent. Is that 2? Very good. 2. You got it. Yeah. In the chat also, I can see that a lot of people, Gonka, Marcos, right? 2, right? You can see clearly, right? The output values are approaching 2, right? From the left. So let's write here 2. Very good. Very good. Once you write your answer, you can share, right? Submit. And then you are ready. We are ready for the next challenge. We're ready for the next challenge. So we click next. Second challenge. Watch this dot as it moves along the function again. What y value is the dot getting closer and closer to as x approaches 1 from the right side now, from the right side? If you know the answer, type it on the chat, so you can say it, right? You figure this out. Welcome the ones who just joined. Here, guys, is the link for you to join to the Desmos activity 1. Clicking that link, please, it's on the chat, and you will be prompted to this this diagram where you can trace or follow where the output values are going from the right now. If we approach the number 1, the input value 1 from the right, where the output values are going? Anybody? I see on the chat. Great, Karen. Yeah, you made my day. Excellent, right? Very good. 3, right? 3. Look, you can see here clearly that it's 3. So let's put it there. So you can see these challenges are not impossible, very reasonable. Yeah, and then you click next. Like that 12 challenges, probably I will go over the 6 or 7 challenges, and then we will go over the lecture. Next question. What is the actual value of y when x is equal to 1? If x is equal to 1, what is the output value associated to 1? Hint, look at this solid circle. Remember, the solid circle is what tells us what is the value, the output value, to be precise, associated to the input value, right? Karen, I think Karen, Ma, also, you guys got it. So let's just type it in, right? Look, clearly this guy, 1, is paired up with midway between 0 and 1, but midway between 0 and 1 is 0.5, right? 0.5. Excellent, guys. 0.5. Submit. And as you can see now, when we go to the next challenge, now this is a summary of what we did, right? From the left, the output values approach 2. From the right, they approach 3. And the actual evaluation is equal to 0.5. So select the option below to see how mathematicians would describe what we saw on the previous 3 screens. This one is this, right? When you approach from the left to the input value 1. This one is when you approach from the right. Remember, limits, they deal with what happened with the output values when you are in the neighborhood of input value, right? From the left or from the right. And then this one tells you what happens exactly at 1. Exactly at 1, the evaluation is 0.5. Great. Next challenge. Now all at once. It says, if all 3 of these values, right? The limit from the left, the limit from the right, and the actual value of the function are the same for a given x value, then the function is said to be continuous at that point, right? If these 3 coincide, the limit from the left, the limit from the right, and the evaluation, it means that they will click, these 2 pieces will click at this solid circle, and then the function will be continuous, right? All in one piece, connected. So is the function shown here continuous at x equal 1? Yes or no? What do you think, guys? Write it in the chat, or you can say it too. I see something on the chat. The students. Very good, Ma. Marcos also. Amei, Gonka. No, right? No, it's not continuous. Not continuous. Very good, very good.
No,
Deep also. Why not? Because remember, we explained that continuity deals with the graph of the function being all in one piece, connected. But you can see that this left piece and this right piece are not connected. There is a gap here. This is what we call it a jump, right? There is a jump discontinuity there. This is the discontinuity. That is why we have to say that at x equal 1, not connected, discontinuous, right? Not continuous, okay? Yeah, so very good. Continuous? No, a big no. Now explain, right? Explain these guys in your own words. You don't have to be technical here or formal. Just say something that will back up your reasoning, right? For example, I can say that I'm a minimalist. So at x equal 1, I would say there is a jump discontinuity, right? As you can see. Continuity. Great, right? That's me. But if you want to be more specific, you can say the left limit doesn't match with the right limit. The evaluation doesn't match with the limit. There are many ways to say this, right? Or you can say that the whole graph is not connected, it's broken at x equal 1. Many different ways, guys. Feel free to let yourself be there. And then at the end, just do this, right? Share with class, share with class. When you share with class, you will get to see what your peers, your classmates have posted, right? For example, here I can see that Gonka posted, no, continuity deals with all in one piece. Excellent answer. I will give you full credit for it. Marcus also, right? No, the limit from the left, the limit from the right, and the actual value of the function are different. Good answer, right? This is formal answer. So cannot be continuous. No, because it's a jump discontinuity. Great, Karen. Yeah, so as you can see, guys, these challenges are not that difficult, right? Just follow your common sense together with what we cover in class, and that should be good. All right, next challenge. Let's see. Let's continue here with the next challenge. This is saying limits. Now, part A. It says, what y value is the function approaching as x approaches 3 from the left? Right? Let's A, part B says, what y value is the function approaching as x approaches 3 from the right? And see what, if any, is the actual y value of x equal 3. So let's answer all these questions, right? All these questions. So let's answer A. If you have the answer for A, let us know in the chat or verbally. For the ones who just joined, here is the link for the activity that we're going through. Just click on the link, write your first name, last name, and you will be in. Okay, so for A, anybody would tell us the answer. What y value is the function approaching the output values, right? As x approaches 3 from the left, right? So when you're
Isn't it
going
negative
down,
1?
you got it, -1. Excellent, right? Look, isn't it that true that we're going to -1? Excellent. Now, for part B, someone else also posted here something. Yeah, deep, very good, -1. Part B now, part B, it says what y value is the function approaching as x approaches 3 from the right, Now you approach from the right this way. Trace where the output values are headed. Gonka, Ma, Deep. Yeah, very good, right? 2, right? 2. You can see here, right? 2. Yeah, excellent. 2. Now, next part C says, what, if any, right? Because sometimes, when you try to evaluate a function at a given input value, the result is not there. What, if any, right? Is the actual y value at x equal 3? Can you figure this out? What is the actual value? And the hint is always look at the solid circle, right? The shaded circle. Excellent, Karen, Miguel, Marcus, right? Yeah, I see, guys, you are tuned. Deep. Yeah, very good, very good. Excellent, right? Look, if you look at this solid circle on the top, 3 pair up with 2, right? Pair up with 2. The bottom has a problem because it's an empty circle, right? Always go with a solid circle for evaluations. So this guy should be 2. Very good. So now let's share with our classmates, our peers, right? And see what was posted, right? The 3 students posted here, right? Versus 2 from the left, the y value. From the right, the value is 2. Okay, good. Feel free, guys, to express your thoughts there. The actual value of y is equivalent to -1. Very good. Yeah, that's okay. That's okay. You can, again, as I said, right? If you create your account in Desmos, as I told, you can adjust your answers, improve it, and I will look at the last submission. Okay, these are meant to, these activities are meant to for you to do that. Now, another thing, guys, that it may help is this. Desmos allows you to give you these tools, right? If you want to kind of trace what's going on when you approach the input value from the left, you can do this, right? Things like this, right? I will look at what you did. I am using the mouse here, right? With this tool, right? So clearly this shows -1 here. Then from the right, you can change the colors. Let's say you use green. From the right, you're going this way, right? From the right, and clearly you are headed, or you are approaching 2, right? 2. The evaluation is, however, a 3 equal 2, right? Because of this solid circle. If you don't like something, you can erase, right? Erase this dot. Yeah. So feel free to use this, guys. This is for straight lines, right? Yeah, very good, very good. Yeah, one more challenge probably, or 2, and then we'll go back to lecture. Now, is the function shown here continuous at x equal 3? Is it continuous at x equal 3? Yes or no? Any question? Anybody? Yeah, and remember, continuity is all about being in one piece. No. Very good, Gonka, very good, Ma, Miguel. Yeah, no, right? Because clearly the graph is broken. Look, here there is what we call a jump discontinuity, right? If you write these type of things, I really appreciate them. Look, for example, you can say jump discontinuity, right? Or just jump. And then this is justifying your answer, right? Jump. Yeah, very good. Very good, guys. So this cannot be continuous, right? It's a broken graph. No. And then, of course, they will ask you to explain. And again, I would say this, right? There is a jump discontinuity at x equal 3, right? That's me. But if you want to use a different support for this answer, feel free to do that, right? Share. You see, I can hear students Marcus answer, right? Because the limit does not exist. Well, anyway, you can justify it if it's consistent with the rules. No, right? Write it out, right? No one is a jump discontinuity very good. No, because there is a jump. Any way you can say it, good. All right, so probably we should go over one more challenge and then go back to the lecture. Let's see. This one. Change the graph by changing, by dragging one of the movable points to create a function that is continuous at x equal 3. Yeah. There is a question here by Marcus in the previous, right? Let's go back to the previous. Marcus is asking, would this function be continuous if we just consider the right piece from 3 to the right? And the answer is yes. This is what mathematicians call a connected component, right? This component is itself, on its own right, is continuous. On the right and on the left, but together as a whole, no, not continuous because there is a jump here, right? But true, good idea. All right, now this is has to do with this applet, right? Move this around, play around with this, and create a function that is continuous. This can be moved too, right? Both can be moved, right? So create a function that is continuous and post your answer. Yeah, very good. Yeah, very good, very good. Yeah, very good, very good. So the good thing about this activity, guys, is that the answers often are not unique. So you can answer this in different ways, as long as it's consistent with what we have studied, what the facts that we have provided in the lecture is okay. For example, here they say, right, drag this point such that the function that is not continuous right here, right, ends up being continuous. Well, again, remember the idea of continuity is the whole graph being all in one piece or being connected, right? So one thing that kind of naturally comes to my mind would be, well, what about this, right? And then I make it continue, right? But that's not the only solution, because someone else could have thought of this, for example, also acceptable, right? Yeah, so there are gonna be different solutions for this, right? So as long as it's connected all in one piece, it should be fine. So let's see, let's see what comes next. Yeah, sketch a function that approaches to 2 different points as x approaches to -4. Yeah, probably I will help you here just with the graph, and then you will answer the questions, right? So can you draw a function that approaches 2 different points as x approaches -4? Look, -4 is here, right? -4 is here. So can you draw a function that approaches to 2 different points as x approaches -4 from the left and from the right? Well, one function that I could think of perhaps could be, let's say I want to approach, yeah, this way here. I could say, if I approach the input value -4 from the left, look at my output values. They're going to this number 2, right? Number 2. And I don't want that to be the same as approaching from the right. So another thing I can do, then I can approach from the right now, so to another point, perhaps this. And here I can have a solid circle, right? Could be empty circle too, doesn't have to be solid, right? But the idea is that this value 5 should be different than this value 2, right? You follow, guys? Look, from here, you are approaching to this value 2, right? If you approach from the left. And from the right, that's not the case, right? That's not the case. From the right, you are approaching to a different value. Let's use a different color. And feel free to use this tool, guys, to draw with the mouse. Yeah, this would be a start, right? And then, of course, you gotta go through all these questions, right? What's the output value approach from the left? What is the output value approach from the right? What is the actual evaluation, right? You can put dots here too if you want to. I just put the dot in here. So feel free, guys, and then write out your answer and then share with your class, right? Okay, guys, so this, I hope, gave you an idea of how you have to deal with these Desmos activities. As I said, I strongly recommend that you create an account in desmos.com. That way, all your work will be safe. So you don't have to redo the activities. Instead, you can improve your results, your answers, right? Very good. All right, so now I think we should go to the lecture, okay? This Desmos activity is in Blackboard, also in our website. So go through it completely. That 12 challenges, I went up to 8.5. Okay, so complete this. All right, so let's close this and let's talk about derivatives. Section 3.1, defining the derivative. Derivative, guys, is considered to be the hero of calculus, the real hero. You may say, Professor, what about limits? Yeah, limits is kind of the building bricks, right? The foundations, but derivatives is really, really in the heart, in the core of calculus, because these derivatives, they're going to be such a great tool for us that even in the end, I will show you how to compute some complicated limits using derivative, right? It's called L'Hopital's rule. All right, so, but now let's explain, right, what these derivatives are, right? It's from the foundations. Let's start first with something that we know very well, linear functions. Let's consider this linear function f of x equals 2x plus 1. When you look at this linear function, the rate of change of this linear function turns out to be constant. And it is not difficult to find it. If you follow rise over run, not hard to see that 2 units for the rise, 1 unit for the run. So the slope of this line, which is change on y values divided by change on x values, expressed as delta y over delta x, is going to be just 2 over 1, right? This is the constant rate of change for this linear function, which is equal to 2. Now, this guy that looks like a triangle is a Greek letter delta, okay? This is a Greek letter delta. Here also delta, and it's used by mathematicians to express change. This is saying delta y means a change on the output values, delta x a change on the input values. But what happens when you deal with lines, linear functions, is that the rate of change is always constant, equal to this guy, which is called the slope, right? The slope determines the constant rate of change. And mathematicians use this approach to model a particle moving in a straight line at a constant speed, right? So let's write it here. This serves to model the following. A particle moving in a straight line at a constant speed, right? This is what this is good for. But now the thing is that in the real world, the universe, things or particles do not move at a constant speed often, right? Instead, they move at a variable speed. So this idea of rate of change through linear functions is very limited. So mathematicians sort of doing this, but not for linear functions, but for any type of functions, not just for lines, for curves. So let's say now, instead of a linear function, we have a quadratic function in the simple form, g of x equal x squared. Let's analyze, just like we did here, the rate of change. Notice that in this case, the rate of change is not constant. This is the first thing what you should notice. It's not constant. Why do you notice that, Professor, so quickly? Well, because notice that it starts flat here, but then gets steeper, right? So the rate of change is not the same for any point, right? It changes point by point, actually, right? gets steeper, steeper here. Here it was just the same steepness, but here it changed. The slope of the tangent line changes, and not only that, changes point by point, point by point. It's like you're driving a car, you're pushing the accelerator, right? The speed is not the same. You speed up, you slow down, right? And this serves to model, for example, particles moving at a variable speed, right? Yeah, it's more useful, this approach. Okay, and particles moving in a straight line, right? Straight line, always straight line at a variable speed. Okay, so now how can we go from here to here? Well, limits will help us. Using limits, we can calculate the slope of these tangent lines that change point by point, right? How? I already gave you an introduction of this idea the first day of class. If you have a curve, let's say a parabola or any curve represented by this, and you set this to be your base point P, where you want to compute the slope, you can do it using limits. How? Well, think of the following. So the slope of the tangent line here should be this, right? The slope of this line. Let's call it tangent line. You can compute the slope of this tangent line by computing the slope of secant lines. So let's draw this here. Let's call it a secant line. But how? How, Professor, are we going to go from a secant line to the tangent line? I already told you about this story before, right? You choose points such that the points are closer and closer to the base point. Eventually, this secant line becomes the tangent line, right? Becomes the tangent line. And I think I have an animation for that. Let me see if it's here. Let me look for an animation. Welcome, the ones who just joined. Yeah, these are formulas. I think the animation is somewhere here. No. It's on our website too. I think I got it here. Yeah, very good. Look how, if you start with a secant line, if you carefully move towards the base point, eventually the secant line becomes the tangent line. You see, guys? Again, you start with a secant line, and you get closer and closer to the base point. Eventually the secant line becomes the secant line. The secant line becomes the tangent line, right? And you can do it from the right and also from the left. Doesn't matter, we're doing it from the right here, right? We're starting here, getting closer and closer to the base point. Play around with that. Animation is on our website. Okay, but the idea is this. The slope of the tangent line is going to be the limit of the slopes of all these secant lines as you choose points closer and closer to the base point. So allow yourself a variation here, small variation h. If you allow yourself a variation h, a plus h should be your new input value. A pair up with f of a via this function. A plus h pair up with f of a plus h. Now take the difference of the output values, f of a plus h minus f of a. On the denominator, take the difference between the input values, right? A plus h minus a. Do the math here, simplify. Take the limit as this h approaches to 0, because notice as h approaches 0, the secant line will get closer and closer to the tangent line, right? So that's the whole idea. So a minus a 0, so h here stays by itself. So this limit as h approaches 0, the limit of this quotient, should be equal to the slope of the tangent line, right? Now, this quotient that you see here is what mathematicians call the difference quotient. Difference quotient. And any function has a difference quotient. Okay? Quotient. Now, the limit of the difference quotient as h approaches 0 is what mathematicians call the derivative. The derivative of the function f of x at x equal a, the base point, right? The base point, this guy, base point. Very good. Okay, the derivative, right, is the limit of the difference quotient. And it's equal, geometrically speaking, to the tangent of the slope of the tangent line, right? It's equal to the slope of the tangent line, geometrically speaking. All right, so now let me show you how, using limits, right, and using this definition for the derivative, we can actually compute the derivative of a function such as this, f of x equal x squared at some input value, x equal 3 in this case, at x equal 3. Solution, we must find the slope of the tangent line, m tan, at x equal 3, our base point, right? At x equal 3, our base point. So what you do is this, the slope of the tangent line is going to be equal to the limit as h approaches 0 of f of 3 plus h, notice this is the base point, minus f evaluated at 3, the difference of the output values. And remember, for the denominator is just h, right? It's just h. So we got to compute this limit using this function, right? Now, the function f of x equal x squared tells you that you have to square the input values, right? Remember, x is just a placeholder. So that function is telling us to this 3 plus h here is square minus the function evaluated at 3 is square. H on the denominator, h on the denominator here. Now, for you to remember this, the base point always goes here and here. Okay? This is this guy. Now, work this out algebraically, right? 3 plus h is square is simply 3 plus h multiplied by itself, 3 plus h, right? Minus 3 squared is just 9 over h. Turns out when you work out these different quotients, there will be always simplifications that will come along. If you FOIL this out, you will get 3 times 3, 9. 3 times h, 3h. I see someone wrote something on the chat. Very good, ma. Yeah, this is where we're headed, right? Yeah, when you FOIL this out, there is even a formula, right, to get this quickly. The ones in the middle, they get added up, right? So you get here twice this, right? 6h, right? But let's just do it sort of from scratch, this, right? When you expand this, FOILing this out, this is what you get, right? Simplifying, as Ma suggested, look, 3h plus 3 is 6h plus h squared minus 9. If you go from here to here, skipping this, it's okay. You just work it out, right? And trying to do it in general so nobody gets lost. Very good. So divided by h. Now you may say, Professor, you promised simplifications. Where are they? Well, here, guys. You see this guy, 9 minus 9, 0, right? 0. Simplifications. Now, distribute the division by h into 6h over h here, h into h squared, which is equivalent to factor out h and cancel h. That also works, right? But let me just distribute this. So we're going to get h into h is 1. So this is 6 plus h into h squared h, right? After simplifying, we get that that's complicated difference quotient ended up being just 6 plus h. Better behave function, right? At that point, when you eliminate this h from the denominator, it's time to stop and try this direct evaluation, remember? So this will be 6 plus 0, which is just 6, right? Which is 6. So this is going to be the derivative of the function f of x equal x squared at x equal 3. At x equal 3. Let's write it out here. So, conclusion, the derivative of f of x equal x squared at x equal 3 is 6, right? It's number 6. The steepness, right, of the tangent line, slope of the tangent line. Now, notation, some notation here. Mathematicians will say that the derivative of f of x at x equal a is denoted as f prime of a. This is how you read this. F prime of a. Let's use this color. This symbol here is the prime symbol. Prime symbol. Try to get used to it. We're going to use this symbol a lot. And this whole thing is read F prime of a. F prime of a. Okay, f prime of a means the derivative of the function at x equal a. So in this case, instead of saying all this in words, the derivative of f of x equal x squared at x equal 3 is 6, I can say, using this notation, the following. F prime 3 equals 6, right? This is what this means, derivative. Okay, guys, so this is how you should compute the derivative using the definition via limits, right? Via limits. Now, probably before we go over the next example, I would like you to practice on the main idea of the derivative, right? As the slope of the tangent line. And for that, I'm going to ask you to go over these two questions that are very straightforward. The first one says, graph first this function y equal negative 2x squared. First graph it. And then draw the tangent line at x equal 1. At x equal 1. So first graph this here. Gonna be a parabola, right? Notice the negative sign will make the parabola open downward. But then graph the tangent line and choose between these 4 alternatives. Can you try this? It's a little bit tricky, I guess, but first I can graph the parabola, and then once you graph the parabola, try to draw the tangent line, right? They just want you to figure that out. The function together with its tangent line. As a hint, let me remind you about this. When you see this sign, negative, this means reflection, right? Reflection. Reflect your parabola. The number 2 means a vertical stretch. Vertical stretch by a factor of 2, right? And this x squared is just a parabola. So the idea, try to start with the graph of the parabola. Just like this, right? Then from there, go to the reflection. Right? Mirror image of this because whatever is positive becomes negative here, right? And then at x equal 1, draw the tangent line, right? Draw the tangent line and match the graph. Yeah, and if there are two candidates, try to use check test points to check, right, which one is the one. Yeah. Yeah, let's do it together, right? Let's do it together, yeah. So this is y equal x squared, a parabola, right? This is y equal minus x squared, parabola opening downward. And the multiplication by the factor of 2, what it's going to do is going to pull this vertically, right? The parabola is going to look like this now, right? This y equal minus twice x squared, vertical stretch by a factor of 2. But now on top of that, they want you to draw the tangent line, right? Let's use a different color. Where? At x equal 1. So this is x equal 1. Get the graph is here and draw the tangent line. More or less it's going to be this, right? This should be the tangent line. But which one is that? Is this this? Is it this? This looks like good candidates, right? This one definitely is not it. This is not it, but these two, between these two. Whenever you're not sure, try to see where this value of x equal 1, is going to take you output y. If x is equal to 1, what should be the output value of 1? Let's put it into our function. Then f or y evaluated at 1 should be equal to, y evaluated at 1 should be equal to, following this function, minus 2 times 1 is squared, right? So y evaluated at 1, the partner of the input value 1 should be just minus 2. This is 1 times negative 2, negative 2. So 1 goes with negative 2. Here, 1 doesn't seem to be going with negative 2, right? Look, this is negative 2. But in this one, yes, look, this guy is going with this guy, negative 2 right there. 1, negative 2. So this should be it, right? Yeah. Yeah, try to follow that, guys. Whenever there are two candidates, use some test points. Could be the y-intercept, sometimes could be take some input value, figure out the output value, and then check on the graph, right? Yeah, very good, very good. Gonka, very good. Yeah, great. Now, this is the first question. The second question, I think, is a little bit easier. It's about estimating the slope of the tangent line based on the fact that the slope of a line can be found using rise over run, right? Rise over run. So for this one, I'm going to give you a nice hint here. Recall that the slope of a line is always gotten as the rise over the run. So basically, try to catch here the rise, the run, cleverly choose 2 points. For example, perhaps this will help. If you choose this point, compute the run and the rise, and then estimate the slope, right? This is a straightforward question. It's just to make the connection between the slope of the tangent line and the derivative. Ma, you made my day. Excellent. Very good, very good. Very good, very good. Look, notice the rise is just 1 unit there. The run, 2 units. So if you do a slope of this tangent line, right? This is the tangent line. Someone else is posting. Yeah, Miguel, Ma. Yeah, let's, excellent, right? Very good, guys. Very good, excellent. Yeah, so rise is 1, run is 2, so it's gotta be 1/2, right? 1/2. This guy. Very good, very good. Yeah, this problem is still with the basic definition of the derivative as the slope of the tangent line, right? Okay, great. So now perhaps we should try to figure out the slope of the tangent line using the definition. I'm going to ask you to do this, and then we will go over the case with the square. Can you find the slope of this tangent line, but using the definition of limits? I will write it out. The slope of the tangent line using this, the limit as h approaches 0 of the difference quotient, f of, remember this guy, the base point 2 goes here, 2 plus h minus f of, again, the base point here, 2, all divided by h. Can you simplify this and get the slope of this tangent line? Go ahead. And then I will give you an example, and I will ask you to do this one, which is a little bit more complicated. And try to follow this definition for the derivative, because on your homework, they're going to ask you to do this. There are going to be some scaffolded questions where you have to show the steps, right? The steps. So try to figure this out. Yeah, and here let me write the next step. This will be the limit as h approaches 0 of the function, this linear function, y equal minus 5x minus 7, right? This linear function evaluated at 2 plus h. So it's going to be this, right? 2 plus h minus 7. This, I'm going to put it within brackets so I don't get confused. Minus the evaluation at 2, also within brackets, the evaluation at 2. There are a lot of negative signs there, guys. So use brackets to keep the order of this. Yeah. This is what you got to do algebraically, right? Simplify, eliminate the h, and then use direct evaluation, and the slope should come out. And if you finish, let us know. Let's see. Question number 3. Marcus, very good. Excellent. Good job. Yeah, it's a little bit tedious because it's computing derivatives using a definition, but it will help us, right, to understand what actually the derivative is. All right, so let's do it together. If you do the algebraic work here, this will become limit as h approaches 0 of negative 5 times 2 is negative 10, negative 5 times h is negative 5h, minus 7, minus 1 times negative 5, positive 5, minus 1, but there's a multiplication by 2, so this will be 10, right? 10, positive 10, right? Minus and minus plus, so plus 7. Professor, you said simplifications will come along. Yeah, here, negative 10 with 10. They cancel, right? 0. So 7 and 7 also, they cancel, 0. So this is just equal to limit as h approaches 0 of negative 5h over h. But h over h is just 0, not 0, 1, right? 1. They cancel. So we end up with a constant function negative 5, whose limit is just negative 5, right? Negative 5. Now, guys, not a surprise. Look, the derivative equal to the slope, right? Equal to the, so when you deal with linear functions, the derivative will be just equal to the slope. Very good, very good. But this is for linear functions, right? But when the function is quadratic, then it's no longer the slope, because indeed the slope of a curve changes point by point, right? It's not constant. All right, we're gonna do this, but let me give you an example first. And we're gonna go a step further, and we're gonna compute not just the slope of the tangent line, but also the equation of the tangent line, okay? So let's go back to our notes. Here is example number 2. It says find the slope of the line tangent to the graph of y equal x squared minus x at x equal 2, part A. Part B, find the equation of the tangent line. All right, so for part A, quickly we say, in order to find the slope of the tangent line, I need to find the derivative of the function, right, at x equal 2. But that derivative of the function at x equal 2 can be computed, right? This f prime at 2, the derivative of the function at x equal 2, as this limit, right? And this is going to be just the slope of the tangent line, right, at x equal 2. Limit as h approaches 0 of what? F of, remember this base point 2 comes here plus h minus f of 2, right? The base point again over h, right? This is the difference quotient. Now we're going to do all this algebraic work. The limit as h approaches 0 of this f of 2 plus h. But f of 2 plus h is going to be what we get when we replace x with this 2 plus h, right? So 2 plus h is squared minus 2 plus h here. Notice how I'm using parentheses and even brackets to keep this organized. This is this first evaluation, right, at 2 plus h. Now minus the evaluation at the number 2. Again, brackets. It's going to be 2 squared minus 2, right? Minus 2. Very good. So all divided by h. Now work this out carefully, algebraically. This will be the limit as h approaches 0 or what? This square is 2 plus h multiplied by 2 plus h, right? Minus distributed over, this is going to give me minus 2 minus h, right? Minus h. This is 4. And 4 minus 2 is 2. So this ends up being just minus 2, right? So this whole thing, 2, minus 2. Now, if you expand this guy, remember the denominator is h, you will get the following. Limit as h approaches 0, or what? 2 times 2, 4. 2 times h, 2h, h times 2, twice h times h squared, right? Minus 2 minus h minus 2. Professor, you promised simplifications, you know? Where are they? Well, here. Notice this 4 cancels with minus 2 minus 2. Minus 2 minus 2 minus 4. Minus 4 taken away from 0, 0, right? 2h plus 2h, 4h. Plus, well, 4h minus h, 3h, right? 3h. 3h there. Plus h squared, right? Simplifying. All divided by h. Now, either factor out h and cancel it, or do what I did before. For the sake of variety, this time I'm going to factor out h for you to see that it's the same, right? H into 3h is 3, h into h squared, h divided by h. Notice you cancel these two guys and you end up with 3 plus h, right? So this will be equal to the limit as h approaches 0 of the function 3 plus h. But this limit can be computed by direct evaluation, right? 3 plus 0, which ends up being just 3, right? So this is the slope of the tangent line at x equal 2. But they don't want just the slope. They want the equation of the tangent line, but with a slope 3 and point 2 to the input value. Output value I don't have, but not hard to find it using my function x squared minus x. So the output value will be 2 squared minus 2, right? which is going to be just 2, right? So with a slope equal 3 and 0.2, 4 minus 2, 2, we can easily find the equation of this tangent line, right? I use this approach. It's called point slope form of the equation of a line. You may use a different method or a different approach, but I use this because this is going to be used in calculus 2, this form. So y1 is 2, slope is 3, x1 again 2. Simplify this and that should be it. 3x here, 3 times 2 minus 6 here, adding 2 to both sides. Y equal 3x minus 4 should be the equation of the tangent line, right? Equation of the tangent line, this equation of the tangent line at x equal 2, right? The derivative of the function at x equal 2, okay? This question now, please do number 5 here. Try to figure this out. Find the equation, not the equation, the equation of the tangent line to the curve at this given point, okay? Now go ahead. So y here, y, try to do this, right? If the equation is y equal x squared plus 3, you're supposed to find the slope of the tangent line using limits. This way, the limit as h approaches 0 of this function. F of base point -4 plus h minus f evaluated at -4 all over h. Figure this out. This will give you the slope with the slope and this point -4, 19. Then you can compute the equation of the line, right? The equation of the line. Go ahead. And this guy is going to help you in homework because they will ask you to do this using the definition of limits, right? The computed derivative. I'm gonna write out the algebraic part of this, okay? So limit as h approaches 0 of f evaluated at -4 plus h in this function should be -4 plus h squared plus 3. Remember, h is just a placeholder, minus the evaluation at 4, bracket here, -4 squared plus 3. I use brackets to keep everything organized because otherwise it's confusing. Yeah, and use your calculator also, right? So help yourself out. And simplification will come along. Okay, guys, let's try to do it together, okay? If you find the answer, just post it in the chat. All right, this guy, -4 plus h squared, remember it's just this, -4 plus h times -4 plus h, right? Then this here plus 3, minus this guy is 16, -4 squared plus 3, 19, right? So this whole thing, 19. So this should be -19. all over h. Someone posted an answer. Let me see. Very good. Yeah, you got it, Ma. Yeah, you got correct this law. Excellent. Yeah, very good, very good. Continue and find the equation of the tangent line, right? Yeah, very good. All right, so then foiling this out and simplifying, remember this is minus 4 times minus 4, 16, 4h plus another negative 4h here, together combining minus 8h, right? When you put these two, negative 4h and minus 4h here, minus 8h, plus h squared. This is what you get when you simplify, minus 19, negative plus 3, this is negative 16, right? And you may say, Professor, where are the simplifications? Here they are. These two cancel, right? So we end up with limit as h approaches 0 of. Again, I'm going to do, for the sake of variety, dividing into, h into each of these two guys. Okay, you can try factorization, also works. All right, so this is going to be limit as h approaches 0 of negative 8 plus h into h squared h. I see someone finished everything. Very good, Ma. Excellent, excellent. Very good. You got it. You got it. Excellent, excellent. Yeah, it's tedious. I agree, right? It's a lot of algebraic stuff, but we're starting with this derivative. All right. So now here you use, after you cancel h, you use the direct evaluation. This is minus 8 plus 0. And as Ma suggested, this is just negative 8. This is the slope, right? This slope, negative 8, together with the point, negative 4, comma 19, should allow me to compute the equation of the tangent line this way, right? Remember, x1, y1 here, y minus y1 equal slope negative 8x minus x1 negative 4, right? It's called point slope form. That's what I use. You may use a different method. It's okay. Negative 8 times x, this negative and negative positive, positive 4 times negative 8 minus 32. Adding 19 to both sides, y equal negative 8x minus 32 plus 19, minus 32 plus 19 minus 13, right? Minus 13. You can do it with your calculator. So this is it. This is the equation of the tangent line at x equal negative 4. Very good. And it's here.